Hey, this is Jackson here for section 1-5 of the Algebra 2 Trigonometry book, which is on equations. Now, evaluating an expression can be thought of as finding out what number the expression equals when you know the value of the variable. Now, for this section, we're going to be doing the opposite. So now we know the value of the expression, but we're going to figure out what the value of the variable must be in order for that to be true. So we're just going to look at a quick example. So let's say we have the expression 3x minus 5 equals 16. So now we know the value of the expression 3x minus 5 is equal to 16. So we need to figure out the value of the variable in order for this expression to be true. Now to do that, we have to look at you basically want the expression to go into the form x equals something. So we have to undo what has been done to the expression. Now this, I'm sure you've done in Algebra 1, but the process is to start by adding 5 to both sides. So we're going to have 3x equals 21 because we're just adding 5 on the left side and adding 5 on the right side, which you can do. Now we're going to divide by 3 on both sides. So x must equal 7. Because, we're multiplying or dividing by 3, multiplying by 1/3, multiplying by 1/3. Now, if you plug 7 back into the original expression, then we would have 3 times 7 minus 5 equals 16, which would be 21 minus 5 equals 16. And then 16 equals 16. So this value of the variable must be true. So now in some cases there may be more than one value of the variable that makes the expression true. So we write the solutions in the form of set notation, which is that s, or set, equals, and then we use the braces. Now in this case there's only one solution, but there could be more, so for this time we'll just write 7. Now, sometimes you're going to find that there's going to be no solution, so there would be no value of the variable that can make the expression true. For example, let's look at the expression x plus 2 equals x. Now, we can't have any value of x for this to be true because you can't add 2 to any number, any real number, and get the same number back. So we're going to say the set equals no solution, and this is the symbol we use for no solution. So now we're going to look at the example. Let's look at an equation that contains a product which equals 0. For example, we have the equation 3x minus 4 times x plus 5 equals 0. Now, we can use one of the field axioms to solve this equation, so we know that for this expression to be either true, one of these products has to equal 0, or both of them could equal 0. So to solve this equation, we can say that 3x minus 4 equals 0, because that would prove this expression to be true, or x plus 5 equals 0. Now we can solve these equations separately. So we have 3x equals 4, we're just adding 4 to both sides, or x equals 4/3, we're just dividing by 3 on both sides. So now for this expression, all we need to do is subtract 5 from both sides, so that means that x equals -5. So to write this expression, to write the solutions in set notations, we're just going to say the set equals, usually you write it in increasing order, -5 4/3. Now, they could list a domain in the original expression. Like, let's say they said they had this expression, but they said that x had to be greater than or equal to 0. If this were the case, then though these are both valid solutions, this would not be the set. We would then say that the set is only equal to 4/3 because that's the only solution that's in the domain. So now we're going to look at an equation that involves absolute value. So the way to think about this equation, the absolute value of x minus 2 equals 3, there's three ways that that could be true. Now remember that absolute value is the distance from 0. So this would mean that inside the absolute value could be -3 or 3 to that be true, because both of those would be 3 units away from 0. So we can set that up and say x minus 2 equals 3. Or x minus 2 equals -3. And then we can solve the equation that way. So then x would be equal to 5, adding 2 to both sides, or x would be equal to -1, adding 2 to both sides. So the solution set of this equation would be set s equals -1, 5. So now we're going to look at extraneous solutions. Now, an extraneous solution is a solution, it's a number in which that satisfies maybe a transformed equation, but not the original equation. So let's just look at the equation x equals 5. Now let's say then that we're going to multiply both sides by x minus 2. So then x times x minus 2 equals 5 times x minus 2. Now this is perfectly valid because we are multiplying both sides of the equation by the same value, so that means that this equation must also be true. Now let's say we plugged in 2 for x, and we said 2 times 2 minus 2 equals 5 times 2 minus 2. Now, multiplying this out, this would be 0 equals 0. Now, this might then lead someone to believe that x equals 2, but the thing is that this solution would be considered extraneous because it is satisfied by the transformed equation, this equation right here, but it is not satisfied by this equation because this equation states that x is only equal to 5. So we're going to say that this is an extraneous solution. So let's say we have the equation x squared equals 4x. Now, someone might approach this problem by first dividing by x, in which case if we divided both sides by x, we would get x equals 4. Now, the reason we can't do that is because when we're dividing by x, we're basically eliminating a solution. We're saying that x can't equal 0, because if you were dividing by 0, both of these expressions would be undefined. So, we're actually losing a valid solution to this problem when you divide by a variable. Now, the appropriate way to do this, if we had x squared equals 4x, the way we want to do this is first subtract 4x from both sides and say that x squared minus 4x equals 0. Then we can factor out an x and say x times x minus 4 equals 0. Then we have this zero product rule again. So for this expression to be true, x could equal 0 or x could equal 4. So as you can see, we have two perfectly valid solutions to this problem, but when you divide by x, you eliminate one of those solutions. So now we're just going to do a couple example problems. So first we have the equation 2x plus 3 equals x minus 1. Now notice the restricted domain here, and we want x to be only positive numbers. This is the notation for that. So the first thing we want to do is add 1 to both sides. So we're going to have 2x plus 4 equals x. Now the next thing we're going to want to do is subtract 2x from both sides. So we're trying to get into that form x equals some number. So that'll be 4 equals negative x. Now if we divide by negative 1, we get x equals negative 4. Now though this value of x does prove this expression to be true, for this solution, we're going to say that there's no solution, because in our restricted domain, x could only be positive numbers, and there's no positive number that could prove this expression to be true. So for this next problem, we have three factors that prove a product to be 0. So to solve this equation, we can set any of these factors equal to 0, because that would prove this expression to be true. So we can say 4x minus 3 equals 0, x plus 2 equals 0, x minus 6 equals 0. So then solving this equation, we'd have 4x equals 3, or x equals 3/4. For this one, we just have to move the 2 over, so x equals negative 2. And for this one, we just have to move the 6 over, so x equals positive 6. Now notice there is no restricted domain given at the beginning of this problem, so when there's no domain given, we assume that the domain is all real numbers. So the solution set to this equation would be negative 2 3/4 positive 6. So that concludes this section on equations. So thank you guys for listening, and I hope this all was helpful. And again, you can find this information in your textbook in section 1-5 if you want to look over more example problems that I went through. And good luck.